Moving to question number 14. Figure shows a rectangular conductor PQRS in which the conductor PQ is free to move in a uniform magnetic field B perpendicular to the plane of the paper. The field extends from x is equal to 0 to x is equal to B and is 0 for x greater than B. So, field x is only in the region x is equal to 0 to x is equal to B. This region alone has a magnetic field and is 0 for x greater than B. X greater than B means beyond B, the field is equal to 0. So, there are two regions. One is x equal to 0 to x equal to B. That region has a magnetic field which is outward. Now, this region x is equal to B to x equal to 2B does not have a magnetic field. Assume that only the arm PQ possesses resistance R. This is the arm PQ. Okay, PQ. And when arm PQ is pulled outward from x is equal to 0 to x is equal to 2B, so it is being pulled from x equal to 0 to x equal to 2B and then is moved backward to x equal to 0 with constant speed V. It is done with constant speed. Obtain the expressions for flux and induced EMF. So we have to find the equations for flux and EMF. Also, sketch the variations of these quantities with the distance 0 less than or equal to x less than or equal to 2B. So basically there are four segments: 0 to B, rightward motion; B to 2B, again rightward; 2B to B, leftward motion; B to 0, that is again leftward motion. So this location, flux is taken on y-axis and position is taken on x-axis. This location is 0, this is B, this is 2B, this is B again, and this is 0. And EMF is taken on y-axis here, position is taken on x-axis. So if you look at the first segment, case 1 is for x is equal to 0 to x is equal to B. X is equal to 0 to x is equal to B means the conductor is sliding on the rail until it reaches the end of magnetic field. Okay, so this movement is inside the magnetic field. So the expression for flux is what? Flux is given by B into area. And area is the shaded area here, which is actually length of the conductor into breadth here. Length of the conductor is L, breadth is B. Because area of the rectangle is length into breadth. So that's going to be phi is equal to B into L into X. B is a constant. It is given in the question. Magnetic field is a constant. Length of the conductor is also a constant. So B and L are constants. So you can remove them by putting proportionality. So we get flux is directly proportional to X. So if you draw the graph of this, flux is directly proportional to X. Directly proportional means the graph will be a straight line that's going up. Straight line with a positive slope. So this is how the graph should be drawn. Flux graph is going straight up in region 0 to B. Why? Because the graph is following direct proportionality. Now, about EMF, EMF is given by minus d phi by dt. That is minus d by dt of, this is called Faraday-Lenz's law. You learned this already. And d by dt of flux is written as B into area. That is minus d by dt of B into, the area covered here is length into breadth. So that will be minus is taken, B is taken outside, length is taken outside. Inside you got dx by dt. Dx by dt is called velocity. So minus BLV. This is the equation for EMF in the first segment, 0 to B. And how about that EMF? B is a constant given in the question. Length of the conductor is a constant. Even velocity is a constant. Constant into constant multiplied by constant will be a constant. But it carries a negative sign. So we are certain about one thing. EMF in the first part is a negative constant. How do we represent that? Constant's graph is a horizontal straight line. Constant's graph is a horizontal straight line. It is negative here. So it should be drawn in the negative quadrant. So negative constant. So that is for the first part. Now moving to the second part. You have to find the flux. Okay. So this is the equation for EMF and equation for flux. Flux is a constant. We got the flux as constant here. And second part, you are moving it from B to 2B. Second segment is from B to 2B. That means outside the magnetic field. The conductor is moved. Actually, this extends until 2B. Okay, so this conductor extends, the rail extends until 2B. So second case is the conductor is moved from x is equal to B to x is equal to 2B. X is equal to B to x is equal to 2B. So in that case, flux is given by B into A as always. But wherever the conductor is, for example, if the conductor is here, the area covered is this much. That means this is the circuit. The circuit covers how much of flux? The circuit has this much of flux associated with it. Even if the conductor is here, same flux is associated with it. This conductor is here, same flux. So no matter where the conductor is, be it here, here, flux will still be the same because the entire flux is linked with the coil now, circuit now. So you can say flux is equal to a constant. So what is EMF in that case? EMF will be minus d phi by dt. That is minus d by dt of flux is a constant from the previous case. Flux is constant. We have learned that d by dt of a constant is 0. Derivative of a constant is 0. So we have two conclusions here. Flux is a constant. EMF is 0 for the second segment. So flux is a constant means the graph will be a straight line, horizontal straight line. Because for a constant, the graph is always a straight line. And EMF is 0 here, which means it has to coincide with x-axis. It has to coincide with x-axis. When y variable is equal to 0, it should coincide with x-axis. So EMF is 0 here. Now, moving on to the third segment, that is, you're moving back to B, 2B to B. 2B to B is actually repetition of B to 2B. Only difference is that B to 2B, you're moving outward, and 2B to B, you're moving inward. The directions just get reversed. Okay, so in that case, I just have to repeat this because, I'm writing it again anyway, third case. This is the third case. This time around, you're moving it backward. X is equal to 2B to X is equal to B. That is still outside. The conductor is here. The entire flux is linked. Conductor is here. Until here, the entire flux is linked. Because when it is here, this is the loop. When it is here, this is the loop. When it is here, this is the loop. All the time, entire flux is linked. So flux will be what? Flux is equal to BA. That does not change. That is equal to constant. So flux will be a constant. Flux is constant. So I can draw the graph this way. For that segment, flux is equal to a constant. How about EMF now? We have learned EMF as minus d phi by dt. That is equal to minus d by dt of flux is here. It is constant. D by dt of constant is 0. So EMF is again 0. EMF is again 0. Right, like this, 2B to B. Now we have the last segment. That means you're moving back to what? From B to 0. So first one was 0 to B, then B to 2B, then 2B to B is also done, B to 0. B to 0 is same as 0 to B because both are inside, right? Inside the magnetic field. The only difference being 0 to B was to the right, B to 0 is to the left. So again, the direction is getting reversed. So let us see that case number 4. Case number 4. So x is equal to, it is moving from x is equal to 2b to, x equal to b to x equal to 0. X equal to b to x equal to 0. How do we do this now? X equal to b to x equal to 0. So it's moving back from x equal to b like this, like this, like this, like this, like this, like this. Okay, right. So first of all, we can write flux. Flux is B into area. That is equal to B into area is L into X. Okay. Since it is going to the left, you must assign direction to it. So it is rather minus X. It is rather minus X. B into L into minus X. I call it minus X. Actually, area is length into breadth. But since you're moving backward to the left, you have to put a negative sign. So you're getting what? Phi is equal to minus BLX. As I have already stated, B is a constant, L is a constant. So I can say phi is proportional to negative of X. Negative of X means what? The graph is again, since it is direct proportionality, the graph is again a straight line. But this time, look at the sign, negative. Negative means negative slope. Negative slope means descending graph. Descending graph means what? It's a graph that's climbing down. So first segment, the graph was climbing up because the motion was to the right. Last segment, the graph is climbing down, descending because it is to the left. And how about EMF now? EMF, you can write it this way. EMF is given by minus d phi by dt. That is minus d by dt of B into L into minus X. Minus of minus plus. B comes outside. L comes outside. What I have inside is dx by dt. So B into L into V. B is a constant. L is a constant. V is also given to be a constant in the question. So that will give you a constant. But it is a positive constant this time. In segment 1, that was a negative constant. In segment 4, this is a positive constant. Okay, it's a positive constant. So it should be drawn this way. So this is the shape of the graph for flux. This is the shape of the graph for EMF. You can even draw the graph for power. How do we get for power? Power is given by E square divided by R. So when you take square of EMF, EMF is negative here, right? When you take the square of it, it becomes positive. So that will be on the positive quadrant, in the positive quadrant. This will be 0 itself. This will be 0 itself. That also will be positive.